All right, so let's get started over here. So this class is entitled Thermal. I know it's one word, but I'm just breaking it in like in two different parts. So what do they call it? Thermodynamics. So thermodynamics is a class that you had to take before, and if somebody was asking you what is the main equation you use in that class, probably your answer will be summation of forces equals to MA. Okay? So in dynamics, what did you do in class? The main goal of the class is to learn how to study the motion of, of a mass or a link or a block or something, no? But if you want is to study the motion. Now, the term thermo is related to what? Thermo is related to basically heat, all right? So over here, you will see on the class note that in thermodynamics, the letter generally used to define heat is the letter Q. So in a certain way, what is the meaning of this class? Is to study the motion of the heat, okay? So over here, what's important is that, you know, sometimes we talk about engineering, mathematics, physics, but what is really physics? Physics is to try to give a mathematical explanation to something that happens physically, you know, to something that's happening in the world. And then the engineers, using those equations, they try to make better that system or whatever the physical equation is studied. All right? So if you want, the goal of the physician is to give a mathematical representation of a problem. The function of the engineering is that now that they know how to do the representation of that physical phenomenon using mathematics, to try to optimize it or make it better or improve it. All right? So let's go back in time. What do you think was the beginning of thermodynamics? Why was people really interested in thermodynamics? So that was a long, long time ago, probably on the, I would say between the 17th and probably early even 20th century. What do you think? Generally, you have the impression that the main problem was motion. You think about locomotives and cars, okay? That wasn't really, it's kind of related, but that wasn't really the main issue in those years. The main issue in those years is that the big cities or the cities were heated using what? Remember, this time, most of the advancements were done over Europe. So in Europe, what was the main source of heating the houses to do everything was coal, no? All right. So coal, generally, you get it from mines. So what happened if you dig a hole on the ground? No matter what, you're gonna get water. Yeah. No matter where you are, okay? So the main problem in those days were like for the mining, and mostly the coal in mining was how to get rid of the water. All right. So initially, what did they have? They had like buckets, and they had generally, you know, like a horse or a mule or something that will go around. All right, and it will pull up through the mechanism, and it will pull up a bunch of buckets from the bottom. All right, and that was the main source of accident. So something that was most important part was how to get rid of the water of the mines. So obviously, when people started to learn about the engines, the main problem wasn't, okay, I need to build a car, was the main application was for mining. How to substitute the little horse or whatever animal was turning around to go and put in function the mechanism that will bring the buckets with water from the bottom. So if you look at all the different patents for the engines, they'll always be related to mining. That's where the big money was, all right? So, and you will see that all of them will probably come from England or the north of France, Germany, Dutch, all that area was the main, the main mining area for coal in Europe, all right? So let's say that thermodynamics, when did it start? Let's say between the 17th And I would say even to the, I mean, let's say 19th century, okay? And the main function was coal mining, and it was basically to the water issue. Okay, and what gave the idea of the engine, of the first engine? What gave the idea actually was something that we know as the pressure cook. Maybe you have seen those ones. What do they do? I mean, if you want to think about it, yeah, I mean, what do they do? Because that's really what thermodynamics is about. What happens if you increase the pressure? So let's say, what is the boiling temperature of water? It's 100 degrees, let's talk about it. It's 100 degrees Celsius, correct? Now, what happens if you put water on the pressure? What's going to happen to the boiling temperature? The boiling temperature is going to increase. So if the boiling temperature increases, that means that the overall temperature inside the pressure cook is going to increase, correct? So, and if it increases, it's going to cook faster, all right? The initial application really of the pressure cook wasn't to cook, was to get rid of, sorry, of all the dead animals, all the bones and all the carcasses. They just wanted to destroy them, not to make like soups and so on, all right? So pressure cook works pretty good for that. All right, but what is at the top? What was the major danger of the pressure cook? Is that the pressure, if you keep hitting it, the pressure inside increases. Okay, so it was one guy. Okay, doesn't matter who was the guy behind the pressure cook. What did he do? What was the big invention? Is that they created a little hole, correct, that had an escape. All right, sometimes you can hear it. It has like a little noise, no? You have the pressure cook, and that will help you to keep the pressure inside the pressure cook more or less constant. Resume recording. So anyway, was the pressure cook, and I was just saying that. So the guy that invented the little pressure relays, he saw that the little thing jelly start turning or start moving up, start making a lot of noise. So there is a lot of energy that is being wasted through that little thing, no? So you find out that if you put like a little mechanism, you can make it go up and down, correct? So you want, that was the whole initial process when they make a thing about the engines, okay? What would be the idea of the engines, okay? The pressure cooker, this energy moving, I can move something up and down, I can use that energy, all right. All right, then obviously once you have the idea, so that was idea for engines. So it's very good to have the idea, but if you don't have any mathematical representation of it, it's going to be very hard for you to make a design of a machine or to improve it. So let's say, how much pressure do I need in order to move this big arm that I want to be able to move that many number of buckets that are going to weigh that much, okay? It would just be a pure guess, no? Or experimental. You have to experiment to do different ones. So you had people that started to define equations. So in 1656, about that area, and you're going to know the name, Boyle and Hooke. This is actually the same guy. If you took solid mechanics, maybe you heard Hooke's law. Okay, it's the same guy. All right, but again, and basically, but what's important over here is that these two persons, through experiment, what did they find out? Is that they find out that if you do the product of the pressure times the volume, this one more or less remained constant. Okay, so that was an advantage. Then later on, a guy called Guy Lussac actually is the one that say, okay, yeah, PV is equal to a constant, but it was also able to relate this to the ideal gas. He kind of developed the ideal gas relation, okay, which is the ideal gas relation. I mean, if you look at thermodynamics, all the names, most of them are either English or French, because in those centuries they were basically the main contributors, okay, and Germany. But Germany was a bit later. Germany was more like on the 19th century, 1819, not on the 17, 18. All right, so just now to give you some names, to give you an idea. So since it was related to mining, really all the first engine came from England. So the first engine, very, very inefficient, but was Thomas Savery. That was really the first engine with application again to mining. Then this name is more common, I mean, and you will know it in Newcomen engine. This one is also, this one was really the first functional engines. Then, I mean, if we get some more, Watt, the same guy as for the units, also developed an engine. Okay, so this is for the engines. Really the guy that is like, if you want, that set up the basics of thermodynamics. I could say two guys, but let's say fathers of thermodynamics. One is Carnot, this one is French, of the 19th century, I think on 1824, 18 something. Sorry. And basically, it's quite interesting because he really set up other foundation for thermodynamics, but he wasn't really able to take it to the next step, which is really to develop the theory, you know? So the theory was really developed by Clausius. So you see a German in this case, okay? And then maybe, but with a lot less important, Kelvin. That obviously Kelvin comes from the units of temperature, okay? So obviously he did something important since they named some temperature under his name. Okay, so we don't have that much left. So 15 minutes. Let me see how much I can. Since I'm just going to give you a quick summary of what we'll be doing. So I think it's interesting to know what people started to get interested in thermodynamics. So what we're going to do in this class is as follows. The first thing we're going to do, and I'm going to do it very quick here, we're going to have more detail next time, is that, and let's think about water. Okay, there is different substances, and probably the most important in all this case is water. So you have water, but you can find water in or at different states, correct? Different form of water. So what are the different states of water? They could be solid as ice, no? It could be liquid, as is most widely used, no, water. And then you could also have water under the form of gas. That would be vapor, okay? So the substance is the same, but you can find it at three different states. So how can you differentiate the state of the water between solid, liquid, and gas? Is it gonna have the same properties? No, okay? So obviously, if you want the same substance, the state of the same substance is going to be defined by its properties. So properties of solid water would not have the same properties as liquid water. The main example, or the easy example, is what? What happens if you fill a bottle of water and you put it in the freezer? What's going to happen? It's going to expand and probably the bottle is going to break. So what property did not remain the same? Density, no? Yeah? Okay? So same substance can be defined at different states, and to know which stage the water is on, you need to look at the values of the properties. All right? So obviously with water it's very easy when we think about at 1 atmosphere, which is the pressure atmosphere. But now, let's say if I tell you, okay, what would be the boiling temperature of water at 10 bars? You have no idea, okay? So in that case, what would be the way to know the state of a substance? Let's see, I'm going to do it from here, would be to go to the properties at the back of the textbook. So for example, let's see, I have all the bunch versions. So let's see if I can find water very quick. I think that's water, A1, A2 is water. So, okay, so let's see if I can close this. This, but 100. So for example, okay, so maybe table A3. No, okay, so bad luck. So maybe, okay, so here you see what would be at 1 bar, what is more or less the boiling temperature is 99.63, so basically 100 degrees Celsius. What would it be at 1.5 bars? Is 111.4. What would it be at 120.2, no? Okay, but, so for example, now, if you know in a problem, they tell you you have water that is at a pressure of 2 bars, but the temperature is, let's say, 115. What would be the state of the water? It would be liquid, no? Because I still not reached the temperature to become gas or vapor. However, you're still thinking about pressure at 1 bar, you're going to say that it was gas, no? Okay? So that's why you need the tables. And the tables, believe it or not, is a lot better than the other solution, which will be to solve differential equations. So basically what you have on the tables is the solution of differential equations. All right? So hold on 1 second. All right, so we're, okay, substance here. Okay, so that's very important in order to know what is the state of a substance. Okay, and so you can do the design. So the first thing we're going to do, the main thing of the class is find here the different properties, substance, define the language using thermodynamics. Then we're going to derive something called the first principle of thermodynamics. Even though the books call it the first law of thermodynamics, I call it the first principle of thermodynamics. It's not a big deal, okay? So this equation here is basically based on, this class is called thermodynamics. So what is the starting equation? Summation of forces equals to MA. And we do division in class, but you did that in dynamics. You can rewrite this under the form of the principle of work and energy, okay? This will become integral of F dr. So what is work? Force times distance, no? And this is equal to what? To the change in kinetic energy. Okay, and this is work over here. All right, so now from here, the division is pretty simple, but we don't have time to do it now. So here, imagine you have work, general work. Now, you might not know what is the work done by a bunch of different forces, but let's think about friction. If you have friction, let's say I rub my hand on this table. I don't know how much work I've done, but the fact of me rubbing my hand on the surface is going to generate what? Heat. Can I measure the heat? Yeah, it's pretty easy, no? So you can see I can find the work done by many forces by just looking at the heat. And I can say this is equal to the change in kinetic energy. Okay, actually it would be potential energy as well. But if there is no energy, if you want, okay, so basically you will see here I mean, I'm going too fast here, but we do that much in detail. So what is a cycle? Cycle is whatever you want. Let's go. We have a process 1, 2, 2, 3, 3, 4, 4, 1. If we start at point 1 and we end up at point 1, what will be the total change in energy? 0, no? Yeah? So for a cycle, well, you will have what? Work plus heat equal to 0. So you will have, I know this is upper the jiggly, but basically you will find that the amount of heat, the amount of work that you can generate will be equal to the amount of heat that you can generate. Or the amount of work or the amount of heat will be equal to the amount of work you can generate.
We can say.
Oh, sorry. Yeah, remind me that. So basically the idea here is what? Is that on the first principle of thermodynamics, which is pretty simple, how can I generate work? By generating heat, okay? And this equation basically is saying that the amount of heat, the amount of work you can generate is proportional to the amount of heat you can generate, which kind of makes sense, no? But is it true or not true? It's not 100% true because nothing is 100% efficient, yeah? So basically the first principle of thermodynamics has deficiencies, and the deficiencies of the first principle of thermodynamics are considered on the second principle of thermodynamics. So the two deficiencies are one that is the efficiency, and this one, I'm going to explain it now. It's very easy to understand, quick, but it's very important to understand. I'm going to repeat it probably 100 times in this class. Is that why a system cannot be efficient? A thermodynamic system is always going to operate between two temperature reservoir, between two temperatures. So for example, if you have your car, your engine running, it is at a certain temperature, but it's running in reference or relative to the ambient temperature, correct? So is the efficiency of your car, of the engine, the same when it's a hot day or a cold day? It's not the same. When is it more efficient? When it's cold or hot?
Cold.
Cold. And what is the reason? Because the more distance at the temperature of your engine to the surrounding temperature, okay, the more work you can generate, no? If you think about it, maximum temperature, minimum temperature, no? The more the farther away they are, the more efficient is the system. The closer they are, the less efficient your engine is, okay? And you agree with me that that is the only way to have an engine that is 100% efficient will be to have the absolute zero, which is not going to happen, no? Okay? So nothing can be 100% efficient. So this is explained. The second one is that some processes can be reversible and some of the processes are called non-reversible, but let me call them irreversible. And here the example I'm going to give you is not 100% correct from the mathematical point of view or physical point of view, but as the explanation, it works very good, okay? So, for example, because basically this is in that you don't need any external action, which it works in one direction, but not the other one. So, for example, if you have water, you can transform the water into ice, and then you can transform back the ice into water, okay? You can transform the water into vapor, and then the vapor from back to the water, okay? So that system kind of look to be reversible, okay? If it's reversible, it means that you are not losing anything, okay? Is that really true? Okay, we'll see. Okay, but that would be the understanding. It's easy to understand. Now, what happens if I take a log of wood and I burn it? I'm gonna get ashes. Okay, now can I get back the log of wood from the ashes? No. So this one will be irreversible. Okay, so what is the mathematical component there is in order to take that into consideration? That one is one that you heard about it and you love to give complicated definition, will be the entropy. Okay, so the entropy will actually take care of the second one. Now, if I ask you what is the entropy, generally the answer I get from you guys is that it's a measure of chaos. I'm like, wow, that sounds very complicated, no? All right, so it's true, but when if you ask somebody to explain it, they don't really know too much to explain it, but really entropy, to make it simple, is a variable that is going to tell you how well you are using the energy that you have at your hand. So for example, if you use very well the energy, your energy, what will be the total change in entropy? 0. If you don't use it well and you have losses, what will be the entropy? It will not be 0. Okay? All right? So that's more the entropy. It's like this is a measure of chaos, yes, because if the entropy is 0, let's say in this room, if the entropy is 0, it means that nothing is happening. Okay? Now, if the entropy is increasing, because it is increasing because we are breathing, no? Our body is generating heat, so what's going to happen? The air molecules are heating up. If they heat up, what's going to happen? The molecules start moving faster, no? If they start moving faster, they generate, due to the impacts, again, they generate more energy. So every time, what's going to happen? Everything is going to start going faster and faster at the molecular way. So everything becomes more chaotic, no? That's why I got to give you that complicated definition, but the reality is a lot simpler than that. It's a quantity that is going to let you measure how well you're using the energy that is available for you at that time. All right? Is it 12:15 the class, or we have 12:30, no? Oh, all right, what's going fast, you see? Oh, good. So now I have 15 more minutes. So we're going to use the entropy. It's good, don't worry. So we have the entropy. So what is the entropy? The entropy actually is defined, almost lost it. The definition is very complicated. Generally use the letter S, and the entropy is defined as, this is delta, but this is, we can say Q, is heat divided by temperature. Good luck, try to understand that. Okay? What is heat divided by temperature? It's entropy, okay? Don't try to understand it. It's like, this is a law. It's not something that is derived, like summation of force equals to MA. There is nothing to understand. It's given to you, no? Yeah? It's a law. This is the same thing. The entropy is a law that was derived by Clausius, but from Carnot, actually. Yes?
Does that say S equals SQ over T?
No, delta. This is like a change in heat. Delta.
Okay, delta. And you have 2 people waiting.
I'm going to call IT and see if they can. So what do I do with them now? I think the reason they did that is to try to lower the bandwidth for the university, but didn't like that. So anyway, it's complicated to understand conceptually the entropy. Okay. Personally, I tell you, who can understand this? Okay. Heat over temperature. All right. What temperature? Would be the one of the surrounding. Okay. Now, another thing we're going to do in this class and that's because most of you are AE probably, and you don't have that class in on the AE curriculum. You have a very good curriculum, but to me, I think you are missing 2 classes. So if you ask me what are the 2 classes you should take for your technical electives, with no doubt, I will tell you one is one class called heat transfer, and the other one is called vibrations. Okay, so the one that is heat transfer, if you want, so the other thing we're going to do in this class to give you some introduction is heat transfer. Because, okay, this is something important. In thermodynamics, really this class is called thermodynamics. Thermodynamics, if you boil water, we don't care how you boil the water, okay? Induction surface, or you do it with a lighter, you do it with whatever you want, okay? You put it in the microwave. We don't care about thermodynamics, don't care about how you provide the heat. The other thing that's important is the amount of heat and how you're going to use it. All right? Now, there's something called heat transfer that now, yes, this part of the class, which is a full class by itself, but here I give you an introduction, it tells you about how the heat can be transferred from one surface to the other. So you are probably familiar with some of them. So what are the three major, the three major heat transfer modes? The most common one is conduction. So let's write the three of them and then we give an example. The second one would be convection. And the third one would be radiation. So now, this is kind of, now this is related, each one of these heats, I think the way to really look at it is that, let's think about three different mediums, okay? And you're probably gonna know the answer of the three of them. You can have mediums. So mediums means whatever is the surrounding where heat can happen. Okay, let's start by the one easier, by the last one. What is the medium in space? There is no medium, so it's vacuum, correct? There is no air, there is no solid, there is no liquid. So what is the way that heat can be transferred in space? By radiation, correct? It's the one answer, but basically under the form of waves. Okay, it's like light. Light is a wave, no? Radiation is also a wave. But what's important here is that radiation happens in a medium that could be, the main one would be vacuum. No medium is needed. Okay, I think about the light. Think about the sun, no? It goes through space. Then it's true that when it comes through the air, there is the air, okay? But it doesn't need it. It can go without it. All right? Now, let's move to the first one. What is another medium that you can find? Solid, no? Now, in solid, what is the way the heat is going to be conducted? By conduction. So an example would be what? So for example, the main example, maybe, most of the problems in the textbooks are what? Either can be the wall of oven, but let's say of a house, okay, in Florida. You have the wall, which is made of, let's say, bricks, hot outside. So the hot is going to impact the brick. Now, how fast the heat is going to go from the outside to the inside is going to depend on the properties, on the insulation properties of your wall, no? Okay? So for example, if you have the first layer, let's say is, I'll do it extremes, is metal. Does the heat transfer quick through metal? Yes, so that would not be a good solution, no? Your house will get hot very quick. Now, let's say, obviously it's never gonna happen. Then let's say after the metal, let's say you have an insulation. So you have, whatever, let's say you have dust of wood. Does the heat transfer good through wood? No, so it's got some kind of insulation, no? Yeah? And let's say after you have whatever, plaster. This plaster, insulator, whatever they are better than steel. Okay? Can you stop the heat from coming in?
No.
No, you cannot. You can slow it down, but you cannot stop it. So what is the whole idea about the insulations? Is that to slow it enough that you get at night, no? And now the system doesn't need to work that hard anymore, no? But you cannot stop it. You can slow it. So there's no such thing like I can stop the heat. Now, and if you want, I can give you the equation. So for this one, would be the form of minus Ka dt dx, but again, we do that in detail. Convection is epsilon sigma t to the fourth minus t to the fourth. And conduction would be HA T minus T infinity. T infinity is still a surrounding. But let's give an example of convection. So convection, what type of medium does it require? So basically it can be liquid. No? So basically we have the three mediums. So it's not that much related to the type of heat. The people have to develop different theories depending on the medium. So now, this is one. I mean, I think I gave you the answer before. If you have a fan in a room, is that fan cooling or heating the room? It's heating the room. Because what are you doing? The fans are moving, they heat the molecule of air, creating friction, no? Friction create heat, no? The little engine inside your fan create heat. Okay? So why do we have them fans? They actually heat up the room instead of cooling it. It's because they move the air. So by moving the air, they make the air going through you move a little bit faster, meaning that now your body can remove the heat faster because there is a flow of wind. Basically, think about you're at the beach. It's whatever, let's say it's 100 degrees Fahrenheit. There is no wind at all. You cannot stay at the beach, no? Now, what happens if you have a little bit of wind? You are less hot. Is the temperature different? No, but what's happening? Because of the wind, your body can remove the heat faster. Okay? So the same thing happens when you put a fan in a room. The fan is actually heating the room, but it feels good because it's helping your body to remove the heat faster. Okay? So let's stop over here. And guys, remember that I will just be creating the link to the class like right at the time of the class, so you can connect to it. Okay?